Whoever's remote, please mute. Cheesy.
Cheese.
Can everybody see the camera?
Looks like, oh yeah, no, I can see everyone. It just looks like a picture of the front row because of
Are you? Well, let's get that out of the way. All right. So welcome everybody to the Spring 2015 Lightning Talks. I think, who's never done one of these Lightning Talks before? We got a few sprinkle around, but most people have. So, you know, normally when I specify the rules, I say it's 3 minutes, but most take 2, and that's a hint to keep them to 2. But this time I decided, no, we got it. The lab has gotten pretty large, so we really need to strictly keep it to 2 minutes. And we're going to be a little bit strict and a little bit rude about that. It's sort of like, what do they call those? Conference chaos minute or crazy minute or whatever they call minute madness type of thing. We've got a tight agenda. We've got 27 possibly plus people. And let's start off the assignment. And we've got some remote people sprinkled around. I'm going to do a backdrop of, I won't bother you guys with, go ahead, get started.
Okay, quickly into my work. It's called Playing Games with Cognitive Computing. So I'm taking the cognitive computing deep question answering pipeline and making it answer games, making it play games. So instead of doing verbal stuff and take all that away, we throw numbers at it, we pass them down the pipeline, and we basically try to handle big, complex games, not chess. That's branching factor of 30. We're looking at games with branching factors in the thousands. So there is no conceivable way you can do this with branching bound. You can't search. The search space is too big. Consider that Jeopardy had a search space that is effectively unbounded. Jeopardy, the search space, if you think about it, you ask one question. The search space is every word in the English language, including proper nouns, abstract nouns, improper nouns, verbs, you name it, combinations of nouns, words from other languages, numbers. Input can be audio, video, lexical, whatever. The search space, boom. You try and do that with a branch and bound, something like A star. It doesn't matter how much you prune it. It doesn't matter how much you trim it. You cannot do it. Watson showed that you could solve the problem of complex search space, of massive search space, and with enough data processing, you could do it in 3 minutes. I'm not doing the data processing. I've got a game. It has an extremely large search space. For one individual move, the order of complexity goes from 1 to 2 to the 89th power. That's the range that we're looking at for one individual move. Not a turn, one move. There is no way you can do that with branch and bound, so you need another approach. So we're taking the pipeline approach. That's one part. The other part, cognitive computing traditionally has some kind of machine learning in it. I am replacing that with a strategy thing, because you have to have some control over how you play the game. With branch and bound, with search tree, that's done by looking through plies. Traditionally, the better score that you have, the further you can look ahead, the more information you have about where the game is going, the better you can choose which move you need to make now that will get you towards that optimum score. With this kind of thing, you can't do that. You have to go back on strategy. You have to try and come up with some other way of doing it. So I call it deep thinking. We take the information that we get out of the game, we have a few pre-programmed strategies, and we try to get the agent to reflect. We try to get it to think about what it is doing and change its strategy if one is not working. It's going to be very dumb, it's going to be very simple, but if we can get it to do this, then we'll get a computer that, all right, we program in strategies, but it can recognize when it's failing, and it can start adapting and trying to use different techniques. That's what I'm doing. I'm playing games with cognitive computing. Thank you. I got up.
All right, so Matt, you need to go live with your video.
Is that good?
Right.
That works until we get a remote.
All right. Ready? Okay. I can't hear anybody there, so I'm just going to go. So my name is Matt Klawan. I work on the Jefferson Project. The Jefferson Project is basically a conservation effort that's being done for Lake George, New York. It's a lake about an hour north of RPI. And as a part of the project, there are lots of sensors that have been deployed in the lake and are going to be deployed in the lake that are collecting a wide variety of data and lots of it. So one of the interesting problems associated with that is getting useful stuff out of that large, diverse amount of data so that the scientists can work with it easily. And one of the ways that we're trying to tackle that is by providing some kind of spatial context to all the measurements that are being taken. That involves associating named locations in the lake with these measurements so that the people operating on the data can interact with regions that they're familiar with. Currently, that's being done through an instance of a solar database, which has these polygons associated with named regions in the lake, and then you can search for data within those named regions. And what that allows you to do is to run some analysis, such as ecological niche modeling, which attempts to predict where certain species can live in the lake. And now that analysis that you performed has some sort of spatial context that a scientist is familiar with, so they can interact with this data and the derived products, like the ecological niche model, using these familiar English names of locations in the lake, and they can search for products and data much more easily. That's about it.
Thanks, Matt. All right. Next is Dominic.
Hi. My name's Dominic. I'm a PhD candidate here at the Royal Constellation, and my project, I guess the name of my talk is Give Peace a Chance, which in this case, Peace is the platform for experimental and collaborative ethnography. So the field of ethnography and cultural anthropology is facing a lot of challenges, similar to some of the challenges other scientific in the natural science endeavors are facing in terms of needing digital infrastructure, needing places to put and repository material, having ways to collaborate online. But what's different with the social sciences and the humanities is they're very different set of challenges that aren't facing natural sciences. They have different types of philosophy, different types of epistemological stances. They have different needs of their data infrastructure that haven't been built yet. And so our project has been trying to find ways of reusing some methodologies and ideas from the deep science methodology from other disciplines, and trying to adapt that and translate that for different sets of social sciences, humanities scholars. So we built an interesting platform to help with these different researchers in modeling their data and doing experiments and sharing primary materials, and then finding different ways to semantify that, be able to share that with others, be able to build different applications from that, and allow them to be able to collaborate and reuse material in ways that haven't been able to before.
All right. Thank you, Dominic. Right. Next is Nidhi. All right, Nidhi.
All right, here I go. Hello, everyone. I'm Nidhi Rastogi. I'm a PhD student working with Dr. Jim Handler. I'm working on two research projects. The first is modeling the propagation of malware attacks in large networks. So this kind of work has not been covered by academia so far. So the approach that I'm taking is understanding current attacks like Stuxnet, DoQ, and Flame, and understanding their properties and how they have spread over the period of several years. First, acting as spywares, and then as real attack, like virus attacks and worms. So I've been going through the literature and understanding their their properties and characteristics in air-gapped networks where not all of the computers in the network are connected to the internet. So they have special properties which cannot be modeled using the traditional SIS and SIR epidemic models. So I'm coming up with my own algorithm, which I'm working on right now, and using mathematical modeling mechanisms to model these specific kind of attacks, which we are seeing more and more in the past few years. The second research project that I'm hoping will turn into my thesis research is identifying anomalous activities in large networks, which are precursor to identifying real attacks. So instead of focusing on just finding attacks happening in large networks, be it homogeneous or heterogeneous, identifying what particular anomalous activities will lead to those attacks and just being able to find them out beforehand. So the approach that I'm taking is using graph analytics and characteristics, basically using graph analytics to understand how anomalous activities in nodes, which are represented by vertices in graphs, can be identified, and instead of focusing on all the nodes at a given time and basically targeting those anomalous activities in all the nodes, using graph centralities to identify specific nodes which are more important in a given time scale, and use the activities taking in those nodes to basically understand an attack that is impending or happening in a given time. So the specific graph centrality that I am focusing on these days is information centrality, and I'm trying to come up with a very specific plan and a specific experiment of how the information centrality will can be how that experiment using information centrality will work out in the kind of in the kind of research that I'm pursuing. So that is it. Thank you.
Thank you, Nettie.
Hi, I'm Eric. I'm working with Professor Hendler. Oh, hi. I'm working with Professor Hendler and some other folks. We're looking at a platform that was developed at MPAC, something called the Campfire, which some of you may or may not have heard about. It's basically a mini 360 screen. It's about 6 feet in diameter, about this high. Inside it, it's a cylindrical display, kind of the first of its kind. It's unlike a big environment where you walk in, there's like projections all around you. It's designed as an object that you kind of walk up to. You can see the inside of the cylinder and the floor as well. And that was developed at MPAC, and now we're looking at different applications and different ramifications of using that type of display as opposed to working in an immersive environment. So there's kind of 3 main areas that we're looking at. Semantic visualizations and things that we can do in that cylindrical display space or pseudo-volumetric display space that you just can't do on a traditional 2-dimensional display. And also looking at the collaborative visualization, collaborative data exploration in that environment, which you also can't do typically on a 2-dimensional display because everyone is staring at the display. Or nowadays, Microsoft even, they have the HoloLens and there's the augmented reality devices. And the problem with all of those is they also cut off everyone's, you don't see eye to eye with anyone. So the nice thing about this particular display and what we're looking at is the collaborative implications of it, because as you look at it, you can also look at other people who are sitting around it and gather around the campfire kind of thing. And then the third part is visualization, collaboration, and cognition. So there are some further follow-on things that we're very interested. There's a lot of talk about cognitive environments or in the cognitive immersive systems where you walk into a room and you talk to the room just like on Star Trek. You say, hello, computer. And instead, we're saying, well, what if there is an object like this that you walk up to and it has a presence and it has an actual situation? So the idea of situated cognition, both in a human-machine kind of level and also a group of people in a situated cognition kind of around an object. So how was that?
That was perfect. All right.
John, can you hear me? Okay, great. Hi, everybody. I'm John Sheehan. I'm a first-year computer science PhD student doing my research work with Professor McGinnis. I wanted to talk to you a little bit about the problem of interoperability in electronic health record systems. We're at a point where we've got medical providers who have systems all over, and yet very often these systems do not talk to each other. So one of the things, I know there's quite a bit of research that's been done already, is how we can use semantic technologies, RDF and others, Sparkle, OWL, to enable not only a very low-level interoperability like a foundational interoperability, which is not something that's new, but real true semantic interoperability where one healthcare system can easily share information with another, even if it uses different terminology, different medical information, maybe in a different language, and yet the systems can interface. So it is an enormous problem. The federal government has put billions of dollars into giving doctors money to buy these healthcare systems, and they're really not realizing the true benefit because they don't communicate well enough. So I think it's an area that's going to be hot in research in the next few years, and hoping to get involved in that. And that's it.
Trying to wait for the to go on mute. Yes, rock and roll.
Hi, everyone. I'm Christine Gloria. I'm a third year, so for 3 years you've heard me hounding about privacy, and I finally have a project that I've tailored my interest and particular knowledge into. This year we're looking at expectations, mostly because I wanted to challenge the idea of what we already know about definitional boundaries of privacy and kind of chasing what that definition might be. So I'm going back to what is from cognitive psychology, expectancy theory, the idea that what you expect will alter your behavior. So we're doing a pretty robust questionnaire looking across experts and novice, understanding what their expectations might be in regards to 3 dimensions of privacy, which are dimensions that no one really goes into, which is your expectation of privacy, your expectation for violations of privacy, and then your expectation of agency. So how much you can actually control what your privacy might be like online. And that's the first set. And then second will be to take that and understand how that maps onto current public policies and whether that challenges our notion of, the Consumer Privacy Bill of Rights, BIPs, etc., and see where they align and where they can't align.
All right, thank you. Hey.
I'm Robin. So recently I've been focusing on kind of a text normalization problem on clinical text, more specifically the intensive text. These texts are actually written by the twin fellows at Mount Sinai Hospital, who is our collaborator for the project. So basically the task is to expand all the operations which are usually frequently used in such kind of clinical notes and texts. And we need to identify such abbreviation and extend them to the proper full expansion, which is returned to the original form of these abbreviations. So the challenging here is in emergency rooms, for example, these abbreviations are hard to understand or expand without certain domain-specific knowledge. For example, like SDAT is used as like urgent or immediately. HX stands for history, and PT is usually used as patient by the doctors. So in order to successfully identify and expand on these abbreviations, the traditional supervised learning methods won't be working for our task due to the lack of training data, because such kind of training data is like very rare results in this domain, and it's very hard to get and expensive to annotate. So we end up with a distributional semantic approach. Use one of the most popular models now called word embedding, and combining it with like the domain-specific resources we gather from either online knowledge base and the domain ontology like Snowman City. So finally, we end up with quite an acceptable accuracy. So I'm rushing on a paper on this topic, and I'm submitting it tomorrow.
Good evening, everyone. This is Corey, and I'm working on a project named Material Processing Ontology. So the focus on processing. So the goal is to develop a framework between the materials processing and material properties and structure. So there are some previous works focused on only just the material structures and properties. So the previous works include set ontology name. The first one is the material science ontology, which was developed in University of Queensland in Australia, and another one is SIO, which is the medical science integrated ontology, which was developed in Stanford, and that was initially used for biomedical research and discovery. So I'm trying to adapt all of these previous work and extend all these ontologies. And because this is some kind of domain-specific topic, I'm also working with some young faculty members from the main department, the academic department, and also the material science department in RPI, try to get some very good use cases, and hopefully the first version will be published very soon.
All right. Yeah, go ahead.
Hi everyone, my name is Anirudh Prabhu. I'm going to talk to you today about one of the projects that I'm working on this semester. It's called Dark Data. The premise of this project is that metadata assets are considered as dark resources or dark data, and we want to be able to use these dark resources which are available in plenty but are not used to the extent that they should be used for. So the plan for this project is to create a search tool which is built on semantic technologies, so that we can explore, visualize, and analyze this data automatically. Giovanni, we're going to use Giovanni for this, and Giovanni automatically does this for you. So this is going to be built. We're going to build a semantic middle layer which has 3 components. It has a content-based image retrieval service, an ontology-based data curation service, and a semantic rules processing engine which helps the data curation service return the correct data granules. So that's pretty much what the project is about. I wanted to run through a use case example for that, like the workflow. I'm going to use the crib sheet for some of the specific data terms which I don't remember. So the use case goes like you're given a list of events. It can be anything from a hurricane to a volcanic eruption to anything. So let's say you're given a list of events and you select the specific event. You select a volcanic eruption, then you're given a list of eruption episodes, and you select the eruption episodes. Based on this information, it selects one of the many phenomenons. So the correct manifested phenomenon is selected for you. An example of the phenomenon is either if you select volcanic eruption, it is SO2 emission or ash plume or elevated surface temperature. Then based on this, the system then determines the correct object property. So the object property examples are aerosol optical depth, atmospheric concentration of SO2, surface temperature, something like that. Based on this, you return the correct data set variables. These data set variables, the examples are MOD08, MOD02, KHM. Sorry, this is a little unfamiliar to me, the data set variables, but based on this, you choose the correct, the system chooses the correct data set variables and then returns the appropriate visualization. So this is the plan for what dark data presents to the user. Thank you.
That's very cool. All right, Evan, I got to get you switched over here.
Okay.
Give me 1 second. What do you think? Oops, we need to mute us.
Okay, I'm just going to assume I can go because I can't hear anybody. So I'm Evan Patton, and I am, I guess, a 6th or 7th year PhD student at this point. I'm not sure which. I just recently defended my proposal, which is on the topic of power-aware reasoning agents. So in the semantic web, we are trying to build intelligent systems that can operate in different contexts. And of course, one of these contexts that is really prevalent today is the mobile device. Based on the fact that almost everybody in the room probably has at least one phone in their pockets, we can clearly say that this is something that we have to be able to address as a community. And as such, I'm interested in understanding what the effects of running these types of algorithms is on the power consumption and energy consumption of our mobile devices. Mobile devices have been growing, their capabilities have been growing at a much faster rate than any other technology because of the experience we have. The processors in particular are growing fast, but the batteries are not. So we have all this additional computing power, but we don't really have enough to drive it. And reasoning technologies, because of their hardness, are often at the forefront of things that need to optimize for processor time and battery, but they don't, processor time and memory, but they don't necessarily do that for battery. And so my work is to understand how different reasoning technologies and different reasoning algorithms can affect energy consumption on these devices, and try to develop new techniques for parallelizing and distributing reasoning tasks so that we can optimize their ability to consume power on a mobile device and thus extend battery life. Thank you.
All right. Hey, Amar. Okay. Just put that in front. Actually, let me grab this first before you do that. Okay, go ahead.
Yeah, hi everybody. This is I'm Amar Viswanathan, and I'm a 4th-year PhD student. So I'm going to talk about knowledge graph error correction. So what is a knowledge graph? These days, all of you are familiar with the term knowledge board. Google builds something on a knowledge board and a knowledge graph. How do they do that? The prevalence of linked data has made sure that we are not. Knowledge. The way you look at knowledge, the way the web is built is interconnected knowledge. So every time you look at a search query, you see linked search results. So how does this happen? You have a lot of information extraction toolkits. Information extraction toolkits give you events, entities, relationships, roles, anything and everything that you can think of. One simple example that I could tell everyone, each one of you, is NEL, the never-ending language learner. What NEL does is just keeps collecting facts all the time. Every day goes to the web, keeps looking for facts. Let's say today it finds something about me on the internet and says, oh, Amar is a graduate student at RPI. Tomorrow it might find something saying Amar is a PhD student at the Federalist World Constellation. So it keeps improving. Now you see that I gave a specific example about Amar. The reason is that there is redundant knowledge all the time. So if you wanted to use every fact that NEL extracts, there is a lot of redundant knowledge. What do you do? How do you sort of correct it? So what we try to do is we convert whatever extracted knowledge is given to us into a graph, use ontological constraints. For example, if the two entities are being named in two different facts, can you merge these two entities? If two entities are disjoint and they're pointing to redundant facts, we want to, remove one of those entities. What do you do with spurious labels? What do you do with entities that are wrong? Can you pick other relationships that can actually, the composition of rules would lead you to the right answer? And so you keep trying to correct your knowledge graph so that it becomes much more complete. Yeah, how do you, at the end of the day, you also want to validate it. So how do you want to validate it? You just traverse through these nodes and see whether each one of these facts that you extracted is consistent all the time. So that's your basis. So every time you go to a set of facts, you start looking for these related facts or the related predicates that each of these nodes are connected to. If they seem to be consistent enough, if they don't violate any of your ontological constraints, then you seem to have a complete knowledge graph. And I think that's...
All right. Thank you very much. No toys this time?
I'm Josh Hilliger, and I'd like to tell you a little bit about incremental continuous partial query evaluation for infinite audio data. So continuous Sparkle is where you have a stream of body of data and you are evaluating Sparkle queries over some subsets of that stream at each point in time. The usual way of doing this is by extending Sparkle with some sort of a window syntax to define that subset of statements. If you don't want to tinker with Sparkle, you usually have to query over the entire stream and accept the fact that you're eventually going to run out of space because you have to index an unlimited stream of statements, even if you only index the relevant statements. So the alternative that I have explored is to annotate the stream of statements with time-to-live metadata. Just as you might do with network packets or with records in a NoSQL database, as each statement comes in, you annotate it with a time-to-live value, say 1 hour, and for the next hour, that statement is considered valid, and it can be used in results, including query answers. After 1 hour, the statements, or rather, all results derived from that statement disappears. Different statements can have different time to live. Another statement may have a time to live of 10 minutes. If you're dealing with very ephemeral data like gesture, you may have time to live of just a few seconds. And the technique scales up pretty well, even at those short time frames. So that's the gist of it. Take a streaming join operator like a symmetric hash join, combine that with some valid time logic and some garbage collection to get rid of expired results, and you have a pretty good way of applying standard Sparkle to implementation.
All right. Thank you. We're doing pretty good on time here. Keep it going.
Hi, this is Lin Yun, fifth-year PhD student in computer science. As part of my thesis proposal, I'm looking at ways to evaluate ontologies in terms of a specific task. So we have a task in mind, and we want to choose the best ontology for the task. Existing ontology evaluation approaches go either very objective but too general. For example, you count the features the ontology uses, or you just use reasoners to check the consistency, completeness, and conciseness of the ontology. Or they can go task-specific but really subjective. That is, you gather a group of experts to specify a set of criteria that is relevant to the task, and then you gather another group of experts to fill out questionnaires to give scores to each criteria. And the approach I'd like to propose is based on the intuition that we need to write software based on the ontology to achieve a certain task. So the better the ontology, the simpler the software could be. And we have mature metrics for software complexity. So we just evaluate the ontology with the software matching that ontology to achieve the same goal. That's it.
All right. Pretty interesting.
Hey guys, this is Carl. The research project I have been working on is called local social event extraction for social media. So the definition of the local social event is like organized by people and attended by a group of people at the same time in the same location for the same purpose. For example, like what we are doing right now, we gather at the Metro building for the TWed lightning talk. So this kind of information will be extremely useful for recommendation systems. And in the research project, we are trying to extract the 5W information for each local social event. So they are which, it means like which type of events it's about. We have predefined 5 types of the local social events. And the second W is called when, so it's just a time And the third W is where, so it's a fine-grained location such as the Windsor building. And the fourth W is called what, so what the event is about, so like the TWed lightning talk. And the last W is who, it means all the participants that attend this kind of events. And traditional methods are not able to be adapted to this problem because of the informal nature of this kind of social media data. So in the project, we propose two novel algorithms to handle the task. The first is we develop the language model-based segmentation method together with the graph-based random walk method to find out the event phrase such as the what and who information. And the second novelty is we use the YAP and Foursquare node base to find out the fine-grained locations such as Windsor building.
All right. So can we just hard code that use case to always recommend to the grad students?
So, hi, I'm Apur. I'm a first year graduate student. So I'm working in the Deep Carbon Observatory project. So there I'm adding a new functionality to the DCO data portal that allows the user to register data type and also to browse data sets using data type. So presently the data sets can be only identified at the syntactic level, like using file types and MIME types. So we are trying to make the data sets that can be identified at the semantic level. So like the two different data sets can have the similar sort of content inside it, and so we are trying to use data types. So when the user is registering a data set, he will be able to associate the data set with the data type, and that data type will have some unique persistent identifier, and also the data type will have some parameters, and it also can also extend from other data types. And the data type will contain other information like source standard and some expected user and other provenance like the author role and the creation time. So to accomplish this, we are following a self-contained architecture where the data types, like we'll be having the data type registry in the DCO data portal, and that will share the data types with the CNRI data type registry, and the CNRI data type registry will have the primitive data types like the data set, image, video, or not. And we are trying to implement a framework that will allow the user to register specific data types, for example, say heat, content, and entropy. So that is more specific to a particular user community. So we are presently so we'll be having a two-level hierarchical federation of data type registry. And so I've created a data type asset in the data set browser where the user can browse the data sets by data type. And also we are planning to have a facility data type browser where the user will be able to browse the data types using different properties. Yeah, that's it. Thank you.
Thank you. And there's a ticket for that. Yep.
Hi everyone, I'm Katie. I'm working on the Jefferson project. I've been working specifically with what we're calling static metadata, the Jefferson project, which is pieces of metadata information that we're not expecting to change much, if at all, during the course of the project, which includes the types of sensors that we'll be using in the lake, the people taking measurements, what those sensors measure, and that sort of like concrete information. So I've been working for the most part over this semester on creating an inventory of this sort of static information, which has included stuff like going through the document specifications for the sensors to record what they all measured and what units, and going back through old data that they've already collected, like George, for the past 30 years, they have some existing data, so going through that and also inventorying what they've already measured. So we can hopefully get all the data together in one place in one format, and look at whatever, we can compare measurements they take tomorrow with measurements they took in the 80s. So hopefully I'll be wrapping that up pretty soon, and then I can start doing cool stuff with solar to make it actually like fun to browse through and look at. So that'll probably be my goal for next semester.
All right. Go Caps.
Thank you. Hi, I'm Laura. I'm also working on the Jefferson Project. And again, the Jefferson Project is a bit like George, and we are trying to make the world's first smart lake. We're installing a network of sensors all up and down the lake that will stream data back so it can be analyzed in real time. And so this is really cool, it's generating a lot of data, but that means it's a lot more work for the research scientists annotating that data with metadata. And we also want to make that semantic metadata so it's really easy to share that data and really easy to process it. That also adds extra time on the side of the field scientists to be doing a really tedious and error-prone format. So we can't have these two things together. It was really annoying our field scientist partners who we want to work with. So I'm trying to solve this problem by automating it for the field scientists by making an Android application for a mobile phone. So it is largely QR code based. So you can scan a QR code that is affixed to an object that will encode its identity, its URI. So simply by scanning objects and then hitting submit, you can generate, the phone generates the appropriate metadata. There's reasoning behind the scenes that the user doesn't have to see, and sending that back in real time. So it does all the tedious work of constructing the metadata and making sure that it's not error prone, so it can do error checks in real time, knowledge base.
All right.
Hi, Howard here, and what I'm recently doing is I'm trying to group phrases and some sentence fragments that express the similar relations between entities together. And as we all know that natural language has very flexible ways to describing relations between entities. So for example, if I want to say somebody graduated from RPI, I can say he graduated from RPI, he got a bachelor degree from RPI, and also he's an alumnus of RPI. So what I'm trying to achieve is I'm trying to find all these similar phrases or parts of sentences cluster them together. And the approach I'm taking that I'm using a hierarchical autoencoder, which is a kind of neural network to learn distributed representations for those phrases. And with this distributed representations, which are basically vectors, and I can use these vectors as the clustering metrics to solve this problem. And so this research topic has some potential usage in earth science domains. So for example, Marshall and I just talked not long ago that. So I got a bunch of papers talking about fossils and geological times. So I can attract some sentences which contain some fossils and geological times, and trying to identify the different relationships between fossils and geological types. And with that, I think I can help scientists a little bit.
All right, thank you. All right.
Hello, my name is Gong Tao, and I'm a second year PhD student in Professor G's group. This semester, I mainly focus on two projects. The first one is event relation. So we proposed the definition and also annotated a large data set for event relation. For example, I want to detect a bunch of stories among the air crash of Malaysia Airlines 17. So, for example, some soldiers push a button, launch the missile, and then the missile hits the plane. That is a temporal relation. And the plane was hit by a missile, and the plane crashed on the ground. That is a causality relation. And also, among these relations, there's one relation called event coreference. It is one very difficult task to detect the coreference. Again, we take the Malaysia accident, for example. So some reporters will say
the plane crashed onto the ground. Some reports will say the plane came down onto the ground. Some reports say the plane fell into the ground. So with current event reference detection system, some will fail because sometimes they think the came down was like a movement, and the crash is like a conflict attack. So they think that they are different. So that comes my second project, which is called event reference with multimedia information. So on the TV program, the reporters will say these three sentences, and often they will come up with a video frame with the plane just crash on the ground. We can search that on YouTube, and we just get the some information. For example, we recognize the object of the plane, and it moves onto the ground, and there's a boom, right? Like the fire and smoke. Then we can know that these sentences are co-referential. They are talking about the same story. Yeah, that's why.
All right.
Thank you.
Oh, stop this. That's Tom.
Hi, this is Tom. I'm a visiting student from China, and in this semester, I was working with Professor Heng Ji, and working on some interesting NLP problems. And the first project I was doing is about automatic generation of topically relevant event chronicles. That is for generating a list of important events about a specific topic in the past. That is very useful for answering some queries to the information retrieval system, such as what important disaster happened in the 2009, and if we want to get the results from the search engine, we have to get such a list that summarizes important disaster events in the past, so that the system can return very good result to users, so that user can have a quick overview of the past events. And in this task, the important things to how to detect, how to rank, and how to summarize the event based on the reference chronicles that is provided in the on the web, on some websites. Because maybe there are some good event chronicles in the past, for example, in 2009, but we want to get the result from 2010, so we use 2009 systems. We use 2009 event chronicles to learn, to detect, to rank, and to summarize events, and to generate the 2010's counterparts. And the experiments shows that our method is very promising. In addition, we are doing some other NLP problems, such as Chinese tense prediction and cross-lingual information network alignment. And I think these are very interesting, and I really enjoy my research.
All right. Yeah. Now we get this. You want this?
No.
Thanks.
Hi, I'm Bassem, 4th-year PhD student working with Professor Hender on GPU parallelization for RDF stores. But today I will be talking about a side idea that I've been working on, which is trusted tweets. So how many times did you follow someone on Twitter, and after a while you start receiving tweets about when is he walking his dog, or when is the birthday of his kid? Now, don't get me wrong, we are not following robots, and human beings tend to talk about different subjects. But with 200 million tweets in one day, it's very difficult, and it's getting very difficult every day. You keep following and you keep scrolling down in your tweet feed just to receive some important news about the field that you are working on. So the idea is quite simple, using LinkedIn endorsements in order to trust the tweets. So if I endorse Professor Hendry, and obviously I do in semantic web, and Professor Hendry endorses John, I can trust what John is telling about semantic web. And there is some node specification. So if I trust John in RDF and Sparkle, I can trust him in semantic web. But I'm not quite sure about oil ontologies, because it's a sub-entity of semantic web, which is a sibling of RDF. So there is 3 phases in the demo. The first one is to collect your LinkedIn connections, to collect your Twitter friends, to do the bonding between the entities, to detect which one is the other. The second phase is to create a network of endorsements. The last phase is to collect your tweets and to do the verification enrichment. So the idea is to get the tweet and to detect the entities that are detected in this tweet. And the last step is to show you only your trusted tweets using the ontology that we built. And I will send you soon a link to trust this, to play with it. And I hope that you trust me in trusting your tweets.
All right, thanks. I like the idea of Jim endorsing me. That's it.
Hello, everybody. My name is Hao. This semester is my starting semester. I'm working on the Deep Carbon Observatory project. And while I was getting used to the detail of the project, I was also working on the data rescue part of the project. And on the micro level, what I do is using the PDF to Excel software to rescue the data from very old dated PDFs into structured data sets. What I propose to do in the future is, well, in the intermediate level, we should be able to enable a way for users to enter the metadata for the data set, and also trying to have some sort of format so the data can be linked with certain known established data types. And on the macro level, I think we should establish a platform which can record the provenance information on the whole data rescue task. Thank you very much.
All right. Good. Let's see.
Hi, it's Steve. This time I'm working on trigger mining for room relation cell type. This task isn't trigger is actually a word that in a sentence that most clearly indicates the existing of a relation or an event. For example, if we want to know a person's children, then the trigger should be son, daughter, stepson, or so on and so on. And in the previous studies, we found that supervised methods are mainly used for this method for this problem. But if we want to set up a new system very quickly for a new relation type, we may fail to find enough annotation data for this task. So we want to try something new. So in our current method, we first separate the task into 2 steps. First, we want to mine some new trigger words as a state, and we want to guarantee the precision. And second, we want to propagate across the whole corpus to generate more and more triggers. And recently, I also have Boolean on the Chinese sort filling task, and we found that triggers are also very important even for Chinese relation extraction. That's it. Thank you.
Thank you.
Hello, this is Sherman. I was actually under before, and I will officially start my PhD next semester.
All right.
So my current work is MD linking, which linking information appearing source to a concept in knowledge base. For example, Wikipedia. So the challenge of this task is ambiguity and variability. For example, I mentioned Washington. It may refer to the state, the capital, the president, even if American government. So our approach focuses on knowledge graph construction. We construct knowledge graph from source based on knowledge representation called abstract meaning representation from USC. And we extract structured information from finally compute the similarity between those 2 knowledge graphs. Our approach is unsupervised. The final performance is compatible with the state-of-art supervised approach, which takes 25K level data. So I think the performance is good.
Hello everyone, my name is Li Fu Huang. My research mainly focuses on concept typing for specific context. For example, URI double key is usually used as a Russian currency for design a libre paradigm, which can be divided into two parts. First is the repetition generation. We generate the general binding from a large size unstructured text and incorporate specific linguistic structures. We generate the computational embedding to capture the specific context information. And then we designed several clustering algorithms to find the different types of the entities. The result seems promising. Thanks.
All right. So give me a second to set up Tim here. Hold on. Hold on, Tim. All right.
Hello everyone, my name is Go
ahead.
Hello everyone, my name is Bolian. I'm a PhD student in Professor G's group, and this semester I've been doing two projects. One is more decoding, which is the opposite one of the project I did in last semester. So Morph is sort of like alias for person or organization, and they exist in social media. So the task is to find the real entity for those morphs, and I used deep learning techniques like to generate word embedding for different for those morph entities, and to compare those entities with compare those morphs with the entities by the cosine similarity, and the results pretty good. And another project I've been working on is Chinese slot fading, and slot fading is kind of like given. For example, given millions of documents, and given a query, and we manually define several slot types like alternate name, date of birth, date of death, and parents, children, those sort of attributes, and we try to find answers for the given query that match these slot types.
Right. And
hey everybody, my name is Ray. So during last year, I've been working on a project called Repurposing Drugs with Semantics. So the motivation of this project is to explore the current existing drugs potentials in order to treat those diseases. On a condition that people previously do not know there is explicit direct interaction between this disease and this drug. So the traditional way of repurposing drugs is basically try to find several chemical compounds and do some experiments against disease cells and see if that compound inhibits or treats that disease cell. So by combining those chemical compounds into the pill, will cause some problems. First one is you never know how much side effects those newly invented pill can cause to the disease and human body when put into a clinical trial. So we come up with a brand new semantic method to achieve that goal, basically by incorporating different databases which contains drug, protein, gene, disease interaction. So for example, in our database, we have drug bank that contains drug versus protein, and ARAF index, which contains a bunch of protein fractions. And then we have almond, which contains protein, gene, and disease interaction. So the beauty of linked data is that when we convert those different databases data and combine them together, you could actually see a beautiful path from the drug to disease. That path is composed by different databases. So with this method, we can actually provide a user interface that allows users to navigate to search, to explore the interactions actually between disease and the protein and drug. So as long as the data set, our database have the information, we will list all of the drug and disease interactions. Basically, they are actually graphs. One node is drug, disease, and protein. They are connected with different pathways. So basically, you could actually explore them by expanding the node from going up and going down, and also could see the interactions strength by see how wide and dense it is, because we also introduced a probability technology that basically help user how possible that interaction could be. So the result is pretty promising. Recently, we have come up with actually 3 potential drugs that is completely new to treat the disease called melanoma, and we are actually doing more work on that.
Good job. I don't know. You look around. Is there anybody else? I think we had about 3 sign-ups during the.
I'm Jim Hendler. I'm a 30th year professor. There were actually 3 reasons why I decided to do this tonight. One is because one of my students challenged me today around lunchtime saying, how come the professors don't do this? And I gave him a lot of lame excuses, but he was right. So in fact, not only am I going to do this, but I invite my colleagues, the faculty here, to join us. Because the students are right. They should hear what we're thinking.
kind of short form. Second reason is some of you were at a talk I gave in Dr. G's class a few weeks ago, where I really was trying to show how there's something starting to happen that's a convergence between what the modern natural language and particularly information extraction technologies can do, what the sort of semantic web and particularly the broader semantics kind of approach can do, what we can do with scalable data, and the new cognitive computing kind of approach to AI. And that when those things somehow reach some kind of convergence, something big is going to happen. I hope listening to these almost 30 talks tonight, you realize that this is a place that can make that happen. So I ask all of you to think about what you've been hearing tonight, and think not just about where your work fits into you, your subgroup, your thesis, but really think about some of the connections you've heard about tonight. Find someone else in the room who mentioned some of the same words you did, and just start talking to each other occasionally. Right? Because I think something can happen. I think this is the place to do it. Which gets me to my third reason, which is the real reason. Because I realized today, I'm looking at some papers in my, I had to send upstairs to the administration. 9 years ago to the day, I signed a piece of paper agreeing to leave the university that I had been at for more than 20 years and come to some small school up in Troy, New York, to try to create something new and different, try to create this thing called the constellation. And I just want to say, looking at all of you guys, thank you, Peter, Deborah, Hung, all of the staff, and particularly all the students. Tonight I feel like I made the right decision.
All right. So I've got nothing else to say. Thank you to everybody. This has been wonderful. Yeah, well, you know me, I do it right now, but no. That's why he said next year. Just a couple of things. So I will make the sign-up sheet, the sign-up hack pad that you all signed up. We'll try to preserve that. We'll link to that from the TWed site so that we can make practical what Jim was suggesting, that you follow up on some of the things you heard. Also, tonight's talk is the minute I stop the broadcast is saved and linked to from the TWed website. That's the advantage of using this new Hangout technology. Thank you for putting up with some of the technical glitches. The people at the beginning, up to about here, who had the projector in your eyes, sorry, but we figured it out. But I really appreciate all of you. You put in a lot of work to put this together. And look forward to we will have special TWeds over the summer. We've already, Deborah and I have solicited a couple students on her side to talk at different points during the summer, more tutorial kinds of things about technologies. Next fall, we're looking to have a slightly different schedule. We'd like some input. It's probably not going to be a regular Wednesday evening kind of thing. It's probably going to be more of either like a Thursday or a Tuesday lunchtime brown baggy kind of a thing. We'd like to have more of the discussion format. One of our goals this term was to have more cross-pollination. And again, this addresses what Jim was talking about. The point of this constellation is the cross-pollination between the groups. We'll continue striving towards that. So thank you for a great term. All right. Yeah, you can't show. If I could get some help, please, taking plates upstairs, put them in rinse them, put them in the dishwasher. Just leave the boxes back there. Just stack them. Thank you. Turn it off. Yeah. And is this your projector? Well, thank you for allowing us to use it. I saw it down here. I said, this is a great projector. Yeah. All right. Thank you for being my co-pilot on the multimedia. Yeah. I got to hit the stop broadcast here.